Hi, we, we will look at the following question. The maximum and the minimum value of x Hermitian Ax for any vector x if A is a Hermitian matrix. Equivalently for a real matrix, if it is equivalent to A being a symmetric matrix. So the answer we will see will be as follows. So for this we will use the property of the Hermitian matrix. So matrix A, if it is Hermitian, so it can be written as V D V Hermitian. So there exists a unitary matrix V such that, so we can write A as V D V Hermitian. So where V is the unitary matrix. By unitary matrix we mean V Hermitian is equal to I and V Hermitian V is equal to I. So in the real if it has the real matrices, equivalently it's a orthogonal matrix, right. And what is D here? D is a diagonal matrix. Moreover, so this V can be constructed using eigenvectors, and this D is a diagonal matrix that has eigenvalues as its diagonal element. Let's say lambda 1, lambda 2, so on, lambda n. This is the D matrix, diagonal matrix. Now, so let's say lambda min is the minimum of all the diagonal values. And lambda max is the maximum of all these diagonal eigenvalues. Now, so if we look at the quadratic expression x Hermitian Ax, now since A can be expressed as V D V Hermitian, we'll use that here. And now V Hermitian x, so let's call it as y. So then what happens to this? So this kind of becomes y Hermitian, right? So that's what it is. So it becomes y Hermitian dy. Now, so since D being the diagonal matrix, so we should note that y is a vector. So y Hermitian is a row vector, y is a column vector. So this is a quadratic expression, so this can be comfortably written as I summation I equal to 1 to n. It has n elements, sum of n elements, and the diagonal elements are there, right, with the eigenvalues. So that would be the eigenvalue times the ith element square. This is how it can be written as. Remember what is y? Y is this V Hermitian x. So if we write it back, so summation I equal to 1 to n lambda I V Hermitian x of the ith element square. Now, so this is what x Hermitian Ax is equivalent to. Now, if you want to find the lower bounds or the upper bounds for this, what should we do? The best thing is, if we can lower bound this by replacing lambda I with lambda min, and we can find the upper bound for this by replacing lambda I with lambda max. So that's what we are going to do. So what are we going to do? So this x Hermitian Ax, which is equivalent to this expression, so can be lower bounded if we replace lambda I with lambda min. So this would be lambda min. Since lambda min, so we can take this out. So what we have is summation I v Hermitian x, the ith element square, this and sum of it. And similarly it would be upper bounded by lambda max summation I equal to 1 to n v Hermitian x, ith element and sum of all the elements square. Right, now let's look at this term, summation I 1 to n v Hermitian x, the sum of square of all the elements of v Hermitian x, right? And if we see it, it's nothing but v Hermitian x L2 norm square, right? And this is nothing but v Hermitian x whole Hermitian into v Hermitian x, and this is equivalent to x Hermitian v Hermitian x, and we know v is a unitary matrix, so this is equivalent to I. So this will give us x Hermitian x. So essentially this term is x Hermitian x. So we can replace x Hermitian x in place of this summation here. So what do we get in the inequality? So we have lambda min x Hermitian x less than or equal to x Hermitian Ax less than or equal to lambda max x Hermitian x. So this is the lower bound of x Hermitian Ax, and this is the upper bound of x Hermitian Ax. The other way of looking at it is by taking x Hermitian x in the denominator of x Hermitian Ax. So we can also write lambda min less than or equal to x Hermitian Ax by x Hermitian x less than or equal to lambda max. And just so you know that this is known as Rayleigh Quotient. And the max and minimum values of Rayleigh Quotient are lambda min and lambda max, the minimum and maximum eigenvalues of that Hermitian matrix. Yeah, let me know if you find any mistakes or if you have any comments. Thank you.